This video is brought to you by mywayteaching.com.
So in this particular part, we are going to study about period and frequency. Okay. See, we already know that any motion that repeats itself at regular intervals of time is called as periodic motion, isn't it? And the smallest interval of time after which the motion is repeated is called its period. Which means if you consider any periodic motion, you can consider this ramp. So after a regular interval of time t, the motion is it's repeating. So this the smallest interval of time after which the motion is repeated is called as period. So in this case, this t is called as period. Okay. So we denote the period by the symbol T. Okay. Capital T denotes period. And its SI unit is given by second. Okay. And for periodic motions, which are either too fast or too slow on the scale of seconds, other convenient units of time are used. Which means if it is very small, we can use microsecond, millisecond, nanosecond, isn't it? So these other kind of units of time or seconds we can use. And the period of vibrations of a quartz crystal is expressed in units of microseconds. As I told you, if it is very small, we can express it in terms of microseconds. So the period of vibrations of a quartz crystal, that will express it in terms of microseconds. Okay. And on the other hand, the orbital period of a planet Mercury is 88 Earth days. And Halley's comet, it appears after every 76 years. And here the reciprocal of t, which means the reciprocal of period, it gives the number of repetitions that occur per unit time, isn't it? So we call that quantity as frequency of the periodic motion. And we represent it with the symbol v, and we can write the relation between the frequency of periodic motion as well as the period like this. The reciprocal of the time is the frequency. That frequency is nothing but the number of repetitions that occur per unit time. Okay. And the unit of this frequency is per second, obviously. And after the discovery of radio waves, Hertz, Heinrich Hertz, a special name has been given to the unit of frequency. So usually we'll say that the unit of frequency is Hertz. Frequency is expressed in terms of Hertz. This is named after a scientist. So 1 Hertz is nothing but 1 oscillation per second. Okay. So 1 Hertz is nothing but 1 oscillation per second. Okay. Now let us see a very simple problem here. On an average, a human heart is found to beat 75 times in a minute. Calculate its frequency and period. Okay, so the beat frequency of heart, if you want to express the beat frequency of heart, then we can write it as 75 by 1 minute. That is nothing but what? 1 minute is nothing but 60 seconds. So which gives an answer 1.25 per second. So we express frequency in terms of hertz. So we can write 1.25 hertz. Okay. And the time period t is the reciprocal of the frequency, isn't it? Which gives an answer of zero point 0.8 seconds. Okay, so it's a very simple problem. We can solve it very easily. So now let us study another important basic concept, that is displacement. Okay, see, we know that the displacement of a particle is nothing but the change in its position vector. So in more general case, or we can say, it refers to change with the time of any physical property under consideration. It can be any physical property. If that physical property under consideration, it changes, we call it as displacement. That change with respect to time. Okay, you consider an example. In case of rectilinear motion of a steel ball on a surface, rectilinear motion of a steel ball which is on the surface, the distance from starting point as a function of time is its position displacement. Okay, from the origin, what we consider that distance, that is called as position displacement. And that choice of origin is a matter of convenience. Okay, and I will give you another example. You can see this figure, a block which is attached to a spring. You can see here, this is a block which is attached to a spring here, isn't it? Yes, and the other end of which is fixed to a rigid ball. So this is the rigid ball. The other end of the spring is fixed to this rigid ball, isn't it? Yes. And generally it is convenient to measure displacement of the body from its equilibrium position. So for an oscillating simple pendulum, the angle from the vertical as a function of time may be regarded as a displacement variable. Okay, you can see in this figure. Okay, an oscillating simple pendulum, its motion can be described in terms of angular displacement theta from the vertical, isn't it? It is described in terms of this angular displacement theta. See, the term displacement is not always referred to the position. Means there can be other kinds of displacement variables. We can say the voltage across a capacitor changing with time in an AC circuit is also a displacement. And in some way, the pressure variations in time in the propagation of sound wave, if you consider, and the changing electric and magnetic fields in a light wave. So, all those physical properties which change with respect to time are displacement variables. Okay, so these are all the examples of displacement in different contexts. See, this displacement variable, it can take both positive as well as negative values. So it can take positive values as well as negative values. So in experiments on oscillations, the displacement is measured for different times. And even we can represent the displacement by a mathematical function of time. See, in case of periodic motion, this function is periodic in time, and one of the very simplest periodic function is given by f of t is equal to a cos omega t, isn't it? If the argument of this function, that is omega t, is increased by an integral multiple of 2 pi radians, then the value of the function remains same. See, the function f of t is then periodic, and that period of is given by t is equal to 2 pi by w. Okay, and this function f of t is periodic with period t. So we can say f of t is equal to f of t plus t, isn't it? Yes. And the same result is obviously correct if we consider a sine function. Here, not only cos, it's true for even sine function. We can write it as a sine omega t. So, a linear combination of sine and cosine functions will be f of t is equal to a sine omega t plus b cos omega t. Okay, and it is also periodic function with the same period t. So we can write a is equal to d cos pi and b is equal to d sin pi. So f of t is equal to d sin omega t plus pi. So here d and pi are constant, and the value of this d is given by square root of a square plus b square, isn't it? And the angle that pi is given by tan inverse of b by a. Okay, so here this d as well as pi, both are constants. See, the great importance of periodic sine and cosine functions is due to a remarkable result which is proved by the French mathematician. He is Jean Baptiste Joseph Fourier, What is that he found? Yes, the Joseph Fourier. Okay, that is, any periodic function can be expressed as a superposition of sine and cosine functions of different time periods with suitable coefficients. Okay, that's what the theory that was found by Joseph Fourier. We can represent any periodic function with a combination of sine and cosine functions of different time periods with suitable coefficients. Okay.